All right, our next speaker this afternoon is Bhavya Gupta, who's joined us from UC San Diego this summer. Bhavya has been working with Peter, and today he'll tell us about their project together, analyzing far-IR oxygen-3 and carbon-2 emission using SOFIA in highly ionized local galaxies.
Thank you, Gwen, for the lovely introduction. And I'm super excited to share what I have been doing this summer. So let's get right into it. So we have this weird mystery of high redshift systems. When ALMA was pointed at highly high redshift systems, which are between Z greater than 6 and somewhere around 9, what we observed was that there was very high O3 over C2 ratios relative to the typical or the normal galaxies. As it is pointed out in Hurricane's 2020 paper, when the luminosity ratios of O3 with C2 were plotted against the SFR, we observed that these red points, which are the high redshift systems, they had very high luminosity ratio of O3 over C2 compared to the galaxies in the blue and the green band over here. We do not know much about why this is happening and what is causing this, but we have few speculations into what might cause the high ratios of O3 over C2 in those high redshift systems. The first possibility that we have is the interstellar medium structure, which is ISM structure, and the gas distribution. Over here is an image of Orion Nebula, which is a high star forming region, which is pretty local. It is in our galaxy, and over here it is the star. This part, the central part, is the star is dominant in star forming, and it produces this O3 gas, which is seen in green over here, which is a high ionization gas, whereas C2 is present in the halo or the outside or the outskirts of this nebular emission, which is low ionization gas or the lower ionization state. Another reason that we think this is because of that the galaxy is completely ionized and there is leaking ionizing radiation from this galaxy, which is causing these ratios to be high. Also, we believe that these stars are young stars and they have very high ionizing radiation fields, which is causing these ratios to be high. Also, a lot of these high redshift galaxies were formed roughly 1 billion years after the Big Bang, which is why they are low in metallicity and they have low C2O ratios, which we believe could be another reason for these high O3 over C2 ratios. So why do we look at local systems? That is because we need to understand the far away galaxies, which are at Z greater than 6. We use local systems such as Z less than 0.1, as they lie roughly within 50 megaparsecs from us or less than that. And as we can see in this image pointed by ALMA, these galaxies are like fuzzy blobs, or it is difficult for the telescopes to resolve the image and also collect a lot of data, which is why we look at local systems. And another reason we explore O3 and C2 is because they are the coolant gas that is produced during star formation, and it helps in radiating energy from the interstellar medium and makes it cool in order to support the star formation. So the main question of my project is, do we see elevated O3 compared to C2 in these local systems? So for our sample, we chose these 4 galaxies: SB2, SB80, SB179, and SB191. And SB over here stands for Shirazi and Brinkman. They selected these 3 criteria to be dominant for selecting these high local systems, which are pretty similar to the high redshift systems. So the first parameter is the high ionization nebular emission, as it was seen in UV for these galaxies, which is very similar to the emission seen in Z greater than 6 galaxies. Another criteria is the young stellar population. These galaxies have very high star formation rate and they are relatively young, which is why we come to this third point, that they're metal poor and they have low C2O ratios. These 3 criteria make these 4 galaxies in general very good local analogs for high redshift systems. My data primarily comes from SOFIA telescope, which is a far infrared telescope, which sits on this Boeing 747 jointly operated by NASA and the German Space Agency. And it flies in stratosphere, which is part of our atmosphere over here. As we can see, the far infrared lines cannot penetrate deeper into the Earth, which is why we need to use this plane to collect data for our, to collect the data, as O3 and C2 are also the far infrared lines. So here is an image of SB179, one of our targets in O3 spectrograph, which is on the left, and on the right, it is the C2 spectrograph with their corresponding spectrums, the emission spectrums over here. And I used a package called SOSPEX, which basically helped me in collecting the flux of O3 and C2 for these galaxies. And I used the Gaussian curve fitting on this central peak over here, which helped me in collecting the flux by finding the area under the curve, as it minimized all other peaks and just gave me the area under this curve, the central peak, to find the fluxes. So backtracking a little bit, when we got our fluxes for SB galaxies, we wanted to compare to some similar kind of survey or similar kind of galaxies that it was looked at. So here comes in DGS. DGS stands for Dwarf Galaxy Survey. It was done by Herschel telescope, which also works in which used to work in far infrared regime. And these galaxies are very similar to my galaxies. However, even though they are like low metallicity and they are like in the local universe like the SB galaxies, what distinguishes the SB galaxies from the DGS sample or the Dwarf Galaxy Survey is these galaxies are very young star-forming regions, and they have very high ionized gas, which was also seen in the UV emissions. And this is what makes these galaxies stand out more, or a better local analog for the high redshift systems. So when we compare the O3 versus C2 flux ratios, where I plotted O3 on the y-axis and C2 on the x-axis and taking the log scale on both the sides, what we observe is that there is a tight correlation between the SB galaxies and the Dwarf Galaxy Survey. And even though these ratios are not exactly 1-to-1, but they are approximately 1-to-1, as we can see in this plot. Next question we had was to look at if C2 is a good tracer for SFR, because when we looked at C2 in high redshift systems, what we observed was that C2 was suppressed, and it was difficult for us to make a conclusion whether it is a good tracer for star formation rate or not. But when we plotted the data for SOFIA telescope for the SB galaxies with the Dwarf Galaxy Survey, we see it is a pretty tight correlation over here. And we can say that the local analogs are not suppressed in C2, and C2 is a good tracer for star formation rate in local systems. Over here, we observe that SB80 is a bit deviated from the trend line, but we believe this could be because how the interstellar medium is structured, which is causing this deviation. Next, we looked at the flux ratios of O3 over C2, which was plotted on y-axis with the metallicity of these galaxies. And the metallicity was measured using this thing called 12 plus log O over H. What we observed was that in Horicon's paper, we know that SB2 and SB179 are the best analogs, local analogs for high redshift systems. So we expected these to be lying somewhere in this blue region over here. However, even though they're relatively low, the ratios, but they're still pretty consistent with the DGS or the Dwarf Galaxy Survey. But we can conclude that they are definitely lower than the ALMA constraints, and we speculate that this is because how the interstellar medium is structured. So coming to my conclusion, the most common conclusion that we came to was that we did not observe nearby highly ionized regions to be elevated in O3 compared to C2. And we can say that C2 is not suppressed in these local systems because there was significant lower ionization emission from the photodissociation region. Photodissociation region is the halo or the outer region of the nebular emission, which is where C2 is predominantly present. And our test of using the high ionized systems with low C2O ratios did not yield us in higher flux ratios of O3 over C2. which is why we need to consider some other parameters to compare the local analogs with the high redshift systems. And for my future works, we plan on using the photoionization models to study the photodissociation region and also work on the uncertainty analysis and upper limit for fluxes. So yeah, thank you.
Questions for Bhavya?
All right, thanks for a great talk. Well done. So you looked at C2 as a function of star formation rate. And I was just wondering what actual measurement is along the x-axis. What are we using to trace star formation rate?
So we use the hydrogen alpha for calculating the star formation rate. And I think this was done by the SDSS telescope, the Sloan Digital Sky Survey, which basically gave me the data for all these galaxies, the SB as well as the dwarf galaxy survey.
Great, thanks.
Yeah.
Other questions?
Is there any physical reason you know of why you might expect carbon-2 to be a good tracer of star formation rate?
I'm not totally sure. That's a really good question, but what we think is, as we can see in this Orion Nebula, what we expect is that O3 is present predominantly closer to the star forming regions, whereas C2 is present in the halo or the outside, and C2 is lower ionization or the lower ionized gas, which is why it is present in the outskirts or somewhere here. And we think it is a good tracer because it is produced during star formation in order to cool the interstellar medium, which is why we think it is a good tracer in local systems, because we found more, not exactly abundance, but like we found more C2 in local systems than in high redshift systems.
I was just curious if you knew maybe any of the other parameters that y'all would be interested in taking a closer look at.
That's a good question. I'm not totally sure because we primarily dependent on actually these three, because these three are the most common ones, because the gas has to be highly ionized and it has to be young stellar population, and it also has to be metal poor. So I'm not totally sure, but I'll get back to you on that.
All right, we should move on. Let's thank Bhavya.